Welcome back to NE 630 nuclear reactor theory. So today we will continue the same business of solving. We already derived the neutron kinetic equation, which is the point kinetic equation. So we'll try to just give some simple derivation for the equation, or simple solution for the equation. So let's continue. So to remind you is the equations again: d by dt for n of t. This is the equation that governs the time rate of change of the neutron population or neutron density, which is equal to rho, the reactivity rho of t, minus beta, and beta here is the Blade neutron fraction for the specific fuel, for example, divided by gamma capital, all multiplied by n of t, plus summation of I equal to 1 to 6 lambda I ci of t. So this is the first equation. Then the second equation is just dci of t by dt equal to beta I, the Blade neutron fraction in the group I, divided by gamma multiplied by n of t, minus lambda I ci of t, and this is again from I equal 1 up to 6. So we showed last time that by using the Laplace transform, we can just transform the set of linear differential equations to a set of simultaneous linear algebraic equation, and we showed that the solution has the form S equal to rho naught, which is rho naught is the initial reactivity, divided by gamma minus 1 over gamma multiplied by the summation of beta I multiplied by S divided by S plus lambda I, and this goes from I equal 1 to 6, and we stated clearly that those are 6, it's a polynomial of degree 7. Yes, guys, so we said that this will be A7 S7 plus A6 S6 plus up to A naught equal to 0. So this is a polynomial of degree 7. We can rewrite this equation. Let's name it equation number 1. So we can take rho naught in one side and get everything in another side. So this will give us rho naught equal to S multiplied by gamma plus the summation from I equal to 1 to 6 of beta I divided by S plus lambda I. So just rearranged this equation to obtain rho naught. Now, if you remember clearly that last time we stated that the solution will take the form of exponential function for both n of t and c of t, and we stated that n of t will be e to the power of st, and c of t multiplied by n naught, and c of t will be c naught e to the power of st. Now from here we knew that S will have how many solutions? 7 roots. So we no longer cannot write that n of t will be n naught e to the power of st. So it will be just a summation. N of t now will be just a summation for I or j equal to 0 to 6. Those are 7 components of aj e to the power of s sub j t, and same for c of t will be the summation from j equal to 0 to 6 c capital of j e to the power of s j t. Again, you'll notice that this is just a0 e to the power of s naught t, a1 e to the power of s1t, a2 e to the power of s2t, up to a6 e to the power of s6t. And same for c of t. So for rho greater than 0 or rho less than 0, we still have those seven roots. So let's look at each one at a time. So for rho greater than 0, if you have rho greater than 0, so we will notice that for rho greater than 0, we will have one root will be positive, and the rest of the roots will be negative. So for rho greater than 0, one root will be positive and the rest of the roots will be negative. So let's assume that S naught will be positive and the rest will be negative. So all of those will do what if they are negative? Will decay away. So you will end up with the initial number of neutrons for positive reactivity insertion. What does it mean, positive reactivity insertion? You take off your control rod, or you added fuel, but the most feasible is taking off the control rod, because you cannot add fuel while you are operating, except for CANDU type reactor. You can refuel while you are running the reactor. So if you take the control rod, for example, you will have e to the power of s naught t multiplied by a naught. So the neutron flux population is increasing with time exponentially, and it has a period equal to 1 over s naught. Why? Because any exponential should have a unitless value. So if this is time, this should be 1 over time. So 1 over s naught is time again. So the period will be 1 over s naught, and the rest of those terms will decay out. So usually you will notice also that this is true for both C and N. This is true for both C and N. So we'll note that N of T and C of T will be finally E naught e to the power of S naught and C naught e to the power of S naught T. So this is just for the solution for what we call the asymptotic solution. Asymptotic mean as time goes to infinity, this should be the values for the N and the C. So how to solve this equation? This is again a 7th order polynomial, and you have to solve it either numerically or you can solve it graphically. How we will solve it graphically? So we'll do the following. Here is the equation that we see here. So all what we will do now is you will notice that if you have any function, for example, we will call this function here, let's say f of s, and this is rho of t, for example, or rho of s, f of s and rho of s. If you plot rho of s, when you plot any function, usually if you take calculus 101, and the way you plot the function is, the first of all, you try to figure the zeros and poles, the zeros and poles of the function. Yes, what are the zeros of the function? Those are the roots of the function. And what are the poles of the function? The points that make the function go to what? Infinity. So you will notice that you have 6 poles. Each one of them is at s equal to negative lambda I. Yes? Yes, guys? So we will do 6 of those. Here is 1. Here is 2. Here is 3, 4, 5, 6. So let's take this one out from here. And then if you will find, let's say, the solution, those will be the poles, and then the 6s, S0, S1, S2, S3, and so on will be the zeros. So one of those zeros, if you plot the function, you will notice that your function is making something like this. Then you have the function like this, like this, so this is again minus lambda 1, minus lambda 2. Those are the asymptotes for your function. 4 minus lambda 5 and minus lambda 6. Those are the six asymptotes for your function. And then the solutions will be the following. This is the right hand side. So if you get to the right hand side equation, this is the f of s. So this equation is f of s. Now, and this is s. The left hand side was what? Rho. So if I have rho equal to 0, rho equal to 0, meaning critical reactor. When rho equal to 0, when you plot rho of s equal to 0, what does mean rho of s equal to 0? This is rho equal to 0. Yes? A function of s equal to 0 mean f of s equal to 0 mean the x-axis. Yes? When I tell you y equal to 0 is what? What's y equal to 0? Equation of what? It's the x-axis equation. Y equal to 0. So rho equal to 0 is the s-axis. Okay, guys. So where will be the seven roots of the function? This is the first one. Yes. So this one. Let's say from 0 to 6. So S0, and this is what? S1, S2, S3, S4, S5, and S6. So we will notice that we have S0, S1 up to S6, 6 roots. Yes? Yes.
Does it always cross the 0? Does S not always cross the 0 point?
Yes. Okay, guys? So S naught is greater than S1, greater than S2, greater than S6. Yes? So if you have your n of t will be equal to a naught e to the power of S naught t plus a2 e to the power of S1t, sorry, a1, plus a2 e to the power of S2t, a6 e to the power of S6t, and c of t the same. It will be c naught e to the power of S naught t plus c1 e to the power of S1t, S2t, so because S1, S2, S3, and up to S6, S1, S2, up to S6, all of them less than 0. Yes? So you will notice that n of t will be what? Nearly the asymptotic solution, e to the power of what? S naught t, and c of t will be what? C naught e to the power of S naught t. So this will be what I just told you 2 minutes ago, that the neutron population will do what with critical reactor? Will depend on the what? S naught. But what's the S naught? S naught is equal to what? 0. So what's n of t and c of t? So your neutron population will be constant with time, and your neutron delayed precursor concentration also will be constant with time. But it will take very very short time to reach to the asymptote, because although S naught is 0 and this is 0, this is A naught multiplied by e to the power of 0 is 1. So this is A naught and this C naught, but A naught plus A1 e to the power of minus S1 t plus A2 e to the minus S2t, and so on. This will take time to decay out. So, yes, and this will take time to decay out. So when you take off from a subcritical position your control rods and move them until you become critical, you will notice in the reactor here that your flux or fission chamber or whatever detector that you are using to monitor the neutron flux inside the core will not stabilize at no time. So let's say you move it from here to here, it will not stabilize at no time. So it will take time, and you will, if you have the blotter in the control room, you will notice that the blotter will go like this, increase with time until you reach to the steady state. So did you understand what happened with rho equal to 0? Okay, what if your rho is greater than 0? So rho of t or rho of s is greater than 0. By the way, the equation that we just stated, the equation for rho equal to beta over gamma, blah, blah, blah. Let me rewrite it again. It's called the Einhauer equation. S multiplied by gamma plus sigma I equal 1 to 6 beta I divided by S plus lambda I. This is called Einhauer equation. Okay, guys? Do you have any question? So for the second case, this is what? S what? S naught. And what is S1? This is what? S1. And this is what? S2. And this is what? S3, S4, S5, S what? 6. And just when you are very close to criticality, S0 is closer to what? 0. And S1 is where? Closer to the poles of the what? Zeros of what? At 0. Okay? But if you are very far away, let's assume you are very far away. So S0 will be somewhere here, and all the S's will at, let's say, at the limit that your row goes to infinity, your zeros will be the same as poles of the, so S1 will be lambda 1, S2 will be lambda 2, S3 will be lambda 3, and so on. So in this case, again, n of t will be what? A naught e to the power of what? S naught of t, and c of t will be what? C naught e to the power of what? S naught of t. And this is for rho greater than 0. So what happened for your neutron population and your delayed neutron precursor concentration? Both will increase with time exponentially. Okay, guys? What if you have now rho less than 0? So this is rho greater than 0, this is rho equal to 0, and this is rho less than 0. So what happened for rho less than 0? So here S0 is greater than 0, S1, S2, S3, up to S6, all of them they less than 0. Yes, guys? So what happened for the other situation here? Your S0 is where?
Lower.
S0. And this is what? S1, S2, S3, S1, S2, S3, S4, S5, S6 here. But what happened for this situation? For rho less than 0. S0, S1, S2, up to S6, all of them are negative. Yes? But which one is bigger? S0 is bigger than what? S1 bigger than what? Bigger than S6. Bigger because if this is negative 10 and this is negative 1, negative 1 is bigger than negative 6. I'm not talking about the absolute value. I'm not talking about the absolute value. I'm talking about the value of the root. So what will happen here? Again, you will have the same situation here, but will be what? N of t will be what? A naught e to the power of minus S naught of t, and c of t, c naught e to the power of minus S naught of t. So what will happen? You will decay with S naught of t and S naught of t. But there is something very interesting here. Let's assume that you insert a negative reactivity. You insert your control rods by a certain level inside your core. So this is S0. Lower the reactivity again. You will be here. Lower the reactivity again. You will be somewhere here. So this is the asymptote. Yes? What does it mean? Mean, even if you go below this one, your period will be restricted by this asymptote. Yes? So if you insert the largest amount of neutron absorber in the world in your core, you will not be able to shut down your reactor faster than this period. So if you have an accident in nuclear reactors and you put the maximum, let's say the maximum amount of negative reactivity inside your core, whatever you will do, you will not be able to shut down your reactor faster than the lambda 1. And I think lambda 1 is something like 80 seconds. Something like maybe 80 seconds or so for uranium, or less than 80 seconds. I don't remember how much. So what does it mean? It means that do whatever you want with negative reactivity insertion, your period, the fastest period will be this one. Okay, guys? Because if this is, let's say, here, this asymptote, let's say negative 6, and negative 1 is here, negative 1 is here, negative 2, negative 3, negative 4, negative 5, negative 6. So e to the power of minus t 6t. Yes? Yes? E to the power of minus 6t. 1 over 6 is the period. So this is e to the power of minus t over 6. 1 over 6 is the period, t over t. So your period will be 1 over lambda 1. Yes? So the shortest period ever will be what? The largest value will be just lambda 1. Yes? So if you are here 1 over 1 is 1, 1 over 2 is half, 1 over 3, the fastest is 1 over 6. So you will not be able to do anything beyond this point. Did you understand? So if I bring this in the exam and I asked you, I give you the graph and I said what will happen at rho is greater than 0, rho is less than 0, rho is 0, and describe at each one what will happen for the reactor and how the reactor will behave and what's the maximum negative period and so on. I brought this example last year in the exam, and although I already discussed it, but not everybody did very well in this. Okay, guys? Yeah, go ahead.
Is there a maximum that you go to, or is there only
A maximum what?
Is there like with p greater than 0? Is there a maximum?
If rho is greater than 0? No.
Yeah.
No, because your rho naught is exponentially, not exponential, it's growing.
So is
Okay.
it like an asymptote at the top?
So this will be, I don't know if there is asymptote or not, but this will be, if you insert more than beta, you will be exponentially growing with Prompt critical. And we will see the situation where you will have the Prompt critical. I will show it to you I think there is an asymptote. Let me plot it for you guys, but give me a second. Okay, I do not know if you will be able to see it here. This is Lamarche. I have it on my iPhone, but maybe more. One more. Yeah.
Oh, looky there.
Okay, guys, did you see it? So this is the negative asymptote here. Did you see this one? So what you see in, I'm sorry I do not have my glasses, but I can do this. So this is the reactor period. okay, in second. And what you see here down is the reactivity, okay guys. And what you see here is it depends on the reactivity. So if the reactivity is positive, so this line here that you see here, this line, did you see this line? It branches to 1, 2, 3 branches. Oops. It branches to 1, 2, 3 branches, and each one of those branches depends on the value for the prompt or the prompt neutron lifetime. So if your prompt neutron lifetime is 1 millisecond, you will get this branch. Okay guys? The second one is your prompt neutron is 0.1 millisecond, which is 10 to the power of minus 4. Okay? Or if your prompt neutron is this one, which is LP equal to 0, meaning that your prompt neutron will just flush away inside your reactor, and it will take 0 time from one generation to the second generation. Very fast. Like what? You expect your this millisecond type of prompt neutrons will be in the what? Thermal reactors, and fast reactors will be less than this one, and between 0 and 10 to the power of minus 4. Yes. So what's the there is an asymptote here. What's the value for the you will see that your period goes very, very fast. Here is your reactor period, and your period goes to what? Goes almost to 0. See, with 0, with your life neutron generation time goes to 0 or is equal to 0, your period goes at certain value for the rho over beta. So what's rho over beta in dollars here? What's this? 1. So at rho over beta at $1, you have what? A prompt critical, and your period goes delve very, very, very rapidly towards 0. But this is up to 10 to the power of minus 3 seconds. Okay? But let's assume we are interested in the case where you have 10th of a millisecond, 10 to the power of minus 4. This is the 10th of a millisecond. Okay? So even if you go with beta equal to let's say $1, which is the activity equal to what? Equal to beta, $1. So if we go $1 all the way up to here, so this period will be what? Will be hitting 10 to the power of minus 1 second, which will be what? tenth of a second, 100 millisecond or so. So did you understand? So this is the curve that I want to show you guys. If you look at the negative reactivity, on the other hand, whatever you will do, whenever you will increase the rho in negative, this is negative reactivity now. What will happen? You become shortest, but then you will hit what? The asymptote, and your asymptote is at what? This is 190, 80 seconds. So this is what I showed you here.
So is the period just like one neutron lifetime, or is that the period that you can bring it all the way down to 0?
No, the period is when your neutron population will double or will go by 1/2. So this is the reactor period.
That doubling time?
Yeah, doubling or half.
Period is E. Factor
Huh?
of E. Isn't
Factor-
period a factor of E?
The period, okay,
Doubling time is
okay. So the period is n of t equal to n naught e to the power of t over t. So your period is whenever your n of t over n naught equal to e to the power of t over t. So this is 1. So e fold. So the period defined as your population. So when your time equal to t, which is the period, your population will go as e folds of your initial population. You are right. So but if your t equal to t2, which is doubling time, your neutron population will double. And double means twice, yes. But e fold is 2 point what? 2.718. So it will be, the period will be much longer than the T doubling. Okay, guys? So did you understand? Oh, sorry. Did you understand this curve? So this curve, you'll find it in Lamarche, both reactor introduction to nuclear reactor theory, and introduction to nuclear engineering. I think this is chapter 7, reactor kinetics. So this is, one second. This is the book, Introduction to Nuclear Engineering, Lamarche. So you will find it there. Okay, guys? So thanks, Mike. So let's now look for the case. Are we done with this? Did you have any questions so far? So I just showed you a graphical representation of what's going on. So now we can look for approximate solution for the Eisenhower equation. Approximate solution or solutions for a point kinetic equation. The point kinetic equation. And one of those approximate solution is one delayed neutron group approximation. And this is similar to the diffusion equation, where we have one group diffusion equation. One group diffusion equation is what? Is the equation that we have been solving for almost all the semester, which is just averaging over all energies. Yes, so it is exactly the same here. You will average over all the six delayed neutron groups, and you will get an effective lambda for those 6 groups, and also you will get effective what? Beta for the 6 group. So beta will be just what? The summation over beta I. Okay, and lambda will be lambda I beta I summation of lambda I beta I divided by beta, as averaging over what? Averaging over. So your lambda effective will be just the summation of lambda I in the group I beta I divided by what? By beta, and this is I equal 1 to what? 1 to 6. And what's your beta? Summation of what? Beta I from 1 to 6. So this is averaging. You average, you get a lambda average for all of them. So now, what will be the equations then? dn by the what? By the t, n of t equal what? Rho minus beta divided by what? Gamma multiplied by n of t, plus, instead of having summation over I equal to 1 to 6, I will have only one what? One group. Yes, so it will be a 1 lambda. And what's the other equation then? d by dt for c of t equal to what? Beta multiplied by n of t divided by gamma again, minus, instead of lambda I c I will have what? Lambda c. Okay, guys? And you expect how many branches here? 2. When I have 6, I have 7. So yes, when I have 6 group, I have 7 what? 7 asymptotes. 6 asymptote and 1. So 1, 2, 3, 4, 5, 6, and 1. Yes? So a polynomial of degree 7. When I have one group only, I will have what? A polynomial of degree what? 2. Yes? So I expect to have this one and this one. And it is as if you have a, do you know the accordion flyers? When you have accordion flyers, so if you open the accordion flyer, you will have all of this. Then when you wrap it, you will have only this, and everything here is gone. Okay, guys? So let's try to solve it here so that I can save this maybe, or you know what, I can replot again. There is no problem. So what's our criteria for solving this equation? What did we do for solving the last equation, the point kinetic equation? We do what? Laplace transform. So we expect to do what? Laplace transform here again. So we'll assume that the solution is in the form of e to the power of st, and then do the Laplace transform again. And you will obtain differentiation with respect to time, so s multiplied by n of s, and here is s multiplied by c of s, and this will be rho minus beta divided by what? By gamma multiplied by n of s plus lambda c of s, and again beta over gamma multiplied by n of s minus lambda c of s, and from this one you can just pick up c of s multiplied by lambda plus s equal to beta divided by gamma n of s, and c of s will be just beta divided by gamma n of s divided by lambda plus s. Take this n of s, c of s, substitute here, and this will give you s n of s equal to rho minus beta divided by gamma n of s plus lambda multiplied by c, which is beta divided by gamma multiplied by n of s divided by lambda plus s. N of s go with n of s, go with n of s, and then you will have s equal to rho minus beta divided by gamma plus beta multiplied by lambda divided by gamma multiplied by lambda plus s. Again, if you just unify those two, this will give you lambda plus s multiplied by gamma, and then lambda plus s multiplied by gamma over gamma, you will have lambda plus s multiplied by rho minus beta. So rho minus beta multiplied by lambda plus s, and gamma rho plus s over gamma rho plus s is 1 multiplied by beta multiplied by lambda, and again this is this equation. If we try to then multiply both sides, so you will have s multiplied by gamma multiplied by lambda plus s equal to rho minus beta multiplied by lambda plus s plus beta multiplied by lambda. If you rearrange, and you will reach to gamma multiplied by s square plus s lambda multiplied by gamma minus S multiplied by rho minus beta minus lambda rho equal to 0. So this is what? S square minus rho minus beta divided by gamma minus lambda multiplied by S minus lambda rho. What's this, guys? Quadratic equation. So again, if you have one delayed neutron approximation, we got a quadratic what? A quadratic what? Equation. So how many roots I will have for quadratic equation? 2. S1 and S2. You will notice that S1 and 2 is just equal to, you will use the normal formula, which is minus p plus or minus the square root of p square minus 4ac, all divided by 2a to solve. So this is, a is what? 1, and b is what? This is b, and c is what? C is minus this. So use this formula. You will get half rho minus beta divided by gamma minus lambda plus or minus 1/4 rho minus beta divided by gamma minus lambda all square plus lambda rho divided by gamma. This is S1 and 2. So they are 1, S1 is this plus this, S2 is this minus the square root of this. Okay, guys? Next time I will show you what does it mean. We will plot the same plot I showed to you. We'll have 2 branches only, and I will show you the case where rho is greater than 0, rho is less than 0, rho is 0. What's the solution for each of those cases, and go from there. Did you have any questions so far? Nothing? Okay. Have a good day.